Hematite. Now, it's something most of us might recognize in its rough, reddish form. A mineral that's been mined and used by humans for thousands of years. But did you ever think this humble iron oxide could become a key player in the future of computing technology? You see, researchers at EPFL have recently uncovered what can only be described as groundbreaking magnetic behavior in hematite. And the exciting part, it's all about something called magnon modes. Now, traditionally in spintronics, that's the field of study where all this happens. Most materials only exhibit one magnon mode, but hematite has this unique ability to support two distinct modes, and that's a big deal. So you might be wondering, what exactly is a magnon mode? Essentially, it's the way that spin waves move and interact within a material. Picture it as magnetic waves rippling through hematite. These aren't just any waves, they carry no electrical charge. That's what sets them apart from the traditional electron-based methods that drive most of today's data storage and processing systems. Here's where it gets fascinating. These spin waves can actually move information around by switching the state of tiny magnets, which serve as memory units. Instead of relying on electron flow, which generates heat and wastes energy, these waves quietly shift magnetization states between, say, a 0 and a 1, enabling the storage of digital information. It's like flipping a magnetic switch without the energy losses that have plagued older technologies forever. And with hematite now showing off these dual magnon modes, it opens up entirely new possibilities. For instance, these modes can interfere with each other, sort of like two voices harmonizing. This interference helps create spin currents that can switch the magnetization of even smaller components in either direction, which could allow us to finally overwrite existing data. So in this single material, we've got something that's not just novel, but also highly efficient, a sustainable alternative for enabling far faster and greener computing. Now let's talk about why this shift to spin waves is such a game changer. Traditional data storage relies on the movement of electrons, and here's the thing. Electrons generate heat. Ever notice how your laptop feels warm after a while? That heat isn't just inconvenient, it's a symptom of energy loss, something we call joule heating. And honestly, it's a real problem when you scale it up to massive data centers. Spin waves, though, bypass this entirely. They don't carry electrical charge, so they don't generate that waste heat. What this means is, we could dramatically cut down on the energy consumption tied to processing and storing data. Cleaner, cooler, and more sustainable. That's the potential here. But how do these spin waves actually work? Well, researchers have managed to harness them using radio frequency signals to manipulate the magnetization of nanomagnets. Picture this, a tiny magnetic unit, like a microscopic switch, flipping between 0 and 1 states. This is the cornerstone of digital data storage, but instead of using electrons, these researchers have found a way to do it via these invisible waves of magnetism. It's incredibly efficient. And one of the most fascinating aspects of hematite specifically is its ability to produce interference patterns in these spin waves. So imagine two sets of waves crossing paths and interacting. Like when water ripples overlap in a pond. In hematite, this interference creates currents that are incredibly precise. These spin currents can be directed to switch magnetization states in ways that were impossible with older materials. This shows us how researchers are not just using hematite for its sustainable properties, but also unlocking entirely new capabilities for processing signals at ultra-high frequencies. The ripple effects, quite literally, could redefine what we imagine for green computing in the future. Now let's dig into why hematite might just be the unsung hero of green computing. Compared to yttrium iron garnet, a material that's been the workhorse of spintronics since the 1950s, hematite is, well, leagues ahead in terms of sustainability. It's more abundant, easier to obtain, and less harmful to the environment, making it a fantastic alternative for future technologies. But this doesn't just stop at being environmentally friendly. The breakthrough around hematite and its dual magnon modes opens up entirely new possibilities for building devices that are faster, smarter, and far more efficient. By integrating these nanomagnets into consumer technology, we could see leaps in how data is stored, transmitted, and even processed. Imagine your smartphone running cooler and lasting longer on a single charge, or your laptop handling tasks at blazing speed without turning into a portable heater. These are the kinds of benefits this technology could enable. Of course, pioneering greener materials like hematite comes with challenges. Moving from lab-based breakthroughs to real-world devices is rarely straightforward. Collaborating with groups like Beihang University has been crucial in uncovering new methods and tackling these hurdles head-on. By working together, they're creating roadmaps to transition these discoveries into practical tools for the tech industry. Tools that could revolutionize entire sectors. So here we have it, an ancient mineral with a storied past now poised to reshape the future of computing. It's a perfect blend of sustainability and innovation, offering us a glimpse of what's possible when science, technology, and creativity converge. And honestly, it's an exciting time to imagine where this could all go. For researchers, for companies, and for all of us who interact with technology every single day. And that's all for today. It's been a fascinating journey exploring hematite and the potential it holds for a greener computing future. Until next time, take care and stay curious.